All right, good morning, everyone. Thank you for being here early, and hopefully all of you are staying warm. We have a record temperature these days. Let me go ahead and go to this week lessons, and I'll share my screen with you. This is week number 5 area. And you can see here in week number 5, you have the overview, which tells you about the learning goals, the lessons we are going to cover, which is 8 and 9, and the chapters in the textbook, if you have the textbook, okay? And the experiment we are going to do, and those are the learning goals that you need to achieve this week from both the lecture and the lab. Okay, the lecture part, the class part, and the lab part. Okay, so if you go back to week number 5, this was the overview. We have 2 assignments this week, quiz number 5 and experiment number 5. Quiz number 5 is over the lessons of the week, which is lessons 8 and 9. If you click on quiz number 5 folder, you have the objectives here, and then you have the videos. Lesson number 8 have one video, and lesson number 9 has also one video, so make sure you watch them. And then we have the reading over the lessons and the solution to the exercises. And here I have also a PowerPoint regarding to conservation of energy. Okay, we might go over it also if we have time. So let's start with the notes here. If you click here on the notes, it will download unit number 2, and from there you can access or slide down to lesson number 8. We'll start with lesson number 8. So that's unit number 2 here. You'll slide down. Last time we covered lesson number 7. So now we're starting with lesson number 8. We'll start, actually, this is the core of this unit. It's over energy and energy form. We'll explain the relationship first between work and energy. We'll classify energy into different categories and subcategories. And then we'll explain what do we mean by the law of conservation of energy. Also, we'll define mechanical energy and explain the conditions of its conservation. So we have the conservation of energy in general, and then we have something called the conservation of mechanical energy. Okay. We'll talk about the quantities that vary in a value to change the mechanical energy. And we'll explain the quantities that vary the value of an object of gravitational potential energy. And then we'll solve problem over mechanical kinetic energy and gravitational potential energy. Those are the goals. So regarding to the first goal here, the definition and the relationship between energy and work, we define energy as the ability to do work. Okay. So for example, an object that is moving has energy. Why? Because if it hit another object, it will be able to apply force on it and move it certain distance. We know that work is force times distance. So any object that has the ability to apply force and move an object distance, we say that this object has energy. Okay, so recall here, recall work is equal to force times distance. Force times distance. So any object has the ability to do work, we say that this object has energy. Okay. And the same thing, work is a way also, or a vehicle by which you change energy from one form to another, and we'll see the different forms of energy and how you can convert one of them to another by exerting work. By doing work, you can change energy from one form to another. Energy has the same units as work, so both of them are in joules in terms of the metric unit, joules. Okay, there are other units of energy that we'll see other than joules. We have, for example, BTU, which is the British thermal unit. We have kilowatt hour, another unit of energy. That's the unit electric company charges us by kilowatt hour. We have calories. Calories is a unit of energy. But the metric unit is joules. Okay, the metric unit of energy is joules. Okay, now let's talk about the energy forms. So this is objective number 2. We'll talk about the different energy forms. There are two major classifications of energy. Okay, and we can let me do it here in the form of chart. So let me just have a space here and I'll talk about that. So energy, which is the ability to do work, energy, can be classified into two major categories. Kinetic energy, and potential energy. Okay, potential. This is the major classification of energy, kinetic and potential. Now, under this classification, there are sub-classifications. Okay, so under kinetic energy, we have several types. So under kinetic energy, you have thermal energy, thermal kinetic energy. Okay, now notice here when we talk about kinetic energy, we are talking about object in motion. Okay, kinetic energy has to do with motion. So thermal energy is the motion of the internal molecules of objects. We know when you heat an object, what will happen, it will gain energy in the form of thermal energy, and that causes the molecules or the atoms inside this object to start moving around. That's why, for example, when you heat water, eventually you see bubbles, and when you reach boiling point, that's when the bubbles reach the surface and explode off the surface. So heating objects is type of kinetic energy. You are giving the object thermal kinetic energy. You are increasing the internal motion of that object. So that's the first type of kinetic energy, thermal kinetic energy. Another type of kinetic energy is electrical kinetic energy, electrical. Electricity is what? Electricity, if you think about electricity, is motion of electric charges. Okay, so when you turn on the light in your room, you are allowing the electric current, which is charges. Electric current is composed of moving charges, electrons namely. You are allowing those electric charges to reach your light bulb and light it on. Okay? So electrical energy is movement of charges. We said that thermal energy is internal movement of molecules due to heating, while electric energy is due to motion of electric charges through conductors, electric wires. Conductors are made of highly conductive materials such as copper that allow the charges to move through it. Okay. So that's the third type or the second type of kinetic energy. Then we have mechanical kinetic energy. Mechanical kinetic energy, which is due to the motion of big objects. Okay, mechanical kinetic energy represents that translational motion from one position to another, like the movement of a car, the movement of an object that is falling, the movement of wheels, and so on. So mechanical energy has to do with actual motion. And we'll focus here more on mechanical kinetic energy among the three types of kinetic energy. Regarding to potential energy is energy stored in the object. Okay, so that's the first thing here. You need to realize that this is energy that is stored. Potential from its name, it has the potential to act. So it's energy that is stored in the object. And we divide potential energy into also sub-classification here, or subcategories. We have gravitational potential energy, that's one. Gravitational. Gravitational potential energy, which is energy due to gravity. When you position an object above the surface of the Earth, you are storing energy in it, okay, in the form of gravity. Of course, it has the ability to fall, so that when you release it, it will have the ability to do work. Okay, remember the common denominator here among all those types is the ability to do work. All those thermal energy has the ability to do work. We know that when you heat water, water will turn into steam. Steam can rotate turbines. When you heat gasoline, for example, inside the engine of your car, when you burn gasoline, gasoline will turn into gases, carbon dioxide and water. And this gas will be able to push on the pistons in the engine of your car, and as a result, it will apply force on those pistons, and it will be translated into the motion of the wheels, and hence you can do work by thermal energy. The same thing, electrical energy. We know electrical energy can operate things. If you turn on your drill, the drill will be able to do work. When you turn on your blender, the blender will be able to do work. So remember, the common denominator among all those types is the ability to do work. That's how we can tell if something has energy or not. The ability to do work. Ability to do work. That's what energy is about. Ability to do work. Okay, so the other type of gravitational potential energy, we said gravitational potential energy because it has the ability, if you place an object above the surface of the Earth and you release it, it will fall, and whenever it falls on something, it will be able to apply force on it and move it certain distance. So gravitational potential energy has the ability to do work. Another type of potential energy is chemical potential energy. And this is energy stored in the chemical bond inside objects, okay? Mainly combustible materials. Combustible materials such as oil, natural gas, coal, okay? Combustible materials hold a lot of potential energy, chemical potential energy. That's why when you release this energy, when you burn it, when you burn coal, oil, it will release this energy and it will be able to do work. Then the third type of potential energy is nuclear potential energy. And that's energy stored in the nucleus of fissionable and fusionable materials, such as uranium. Uranium is fissionable material, hydrogen is fusionable. And actually, if you think about it, nuclear potential energy is the energy responsible for our planet. Why? Because this is the energy that comes from the sun. The sun, the source of energy in the sun is nuclear fusion. Nuclear fusion takes place inside the core of the sun, where hydrogen is fused into helium, mainly. That's the main fusion process inside the sun. Hydrogen fused into helium. And during this fusion process, a huge amount of energy is released from the nucleus. and this energy is transferred into electromagnetic waves. And I forgot here, by the way, under kinetic energy, we have a fourth type, which is electromagnetic waves, light. Let me add this one here into the kinetic energy. So under kinetic energy, we have electromagnetic wave, EM, which is light. Okay, electromagnetic wave, light. Light is considered kinetic energy because light is motion of photons. We call it photons. Photons is the particle nature of light. And we know that light has the ability to do work. How do we know that? We use it in photovoltaic cells, in solar cells. When the light hit the photovoltaic cells, it will what? It will release electrons, release electric charges, because it applies force on the electric charges and cause it to move distance. We know that light has the ability to do work, okay, in photovoltaic cells, in solar cells, and so on, solar panels. So those are the 7. We can actually, all type of energy, we can put them in one of those 7 categories, okay? Thermal kinetic energy, electrical kinetic energy, electromagnetic kinetic energy, mechanical kinetic energy, gravitational potential energy, chemical potential energy, and nuclear potential energy, okay? And those types of energy can be converted from one form to another. As we mentioned here, for example, if you look at the sun, just here to give you an example of energy conversion, inside the sun, what will happen? Inside the sun, we have nuclear potential energy. Okay, so let's start here. The first thing here is nuclear potential energy. That's number 1. Now, this nuclear potential energy will convert into what? Into light. So the sun will, what will reach us from the sun is mainly light. So the first conversion is converting nuclear potential energy into electromagnetic radiation, into light from the sun. Now what will happen? This light will reach us on the earth, and it will help in what? It will help in what we call the photosynthesis of plants. Plants use the light that reach it from the sun to do what? To build itself and build, of course, all type of vegetables, fruits, and so on. So this is chemical potential energy. Food, actually, food in general. Why do we eat food? We eat food because it has chemical potential energy. This chemical potential energy that we consume it and digest it, it will turn inside our body into another type of chemical potential energy, which is food, which is fat, basically. Of course, the food that we digest turn into ATP, and the ATP is energy that will be stored also in the form of fat inside our body. And then we use this fat to do what? To do work, right? To do work. So we can use this fat to run, for example. When you run, you change your energy to mechanical kinetic energy. Okay. When you do any type of physical work, you are doing mechanical kinetic energy. You can lift things. When you lift things, you are basically doing gravitational potential energy. So when you hold something and lift it, you are giving it gravitational potential energy. Also, during this process, you are sweating. Okay, when you do work, when you run, when you do physical work, you are sweating, and sweating is increase the temperature. So it will be changing also to thermal kinetic energy. So you can see here we started with nuclear potential energy, and everything turned into all types of energy, even electrical energy. I mean, if you, for example, if you rub your hands, you are basically creating a static, okay, static on your hand, or friction. And when you do friction, any type of friction, you are developing static charges. So also you can turn the mechanical kinetic energy into electrical energy. Okay, so all that came from where? From the nuclear potential energy in the sun. That's the source of all energy. Now, during this process, the energy will be conserved. So when energy turns from nuclear to electric, the amount that turn from nuclear will be equal to the amount that turn into electric, meaning energy can neither be destroyed nor created. You cannot destroy energy, you cannot create energy. You can only change it from one form to another. Okay, you can only change it from one form to another. So we have the source of energy, which is the sun, and the energy that comes from the sun is turning into all these types. Okay, all these types of energy. The other thing here we'll focus on is something called the total mechanical energy. Okay, total mechanical energy. And that's basically the mechanical plus gravitational. So if you add the mechanical kinetic energy to the gravitational potential energy, if you add those two, the sum of those two, we call it the total mechanical energy. Okay, total mechanical energy. Now, what's special about those about total mechanical energy? The special thing about the total mechanical energy, it's conserved unless there is friction in the system. Okay, so total. And by the way, guys, the term conserved means it maintains its value. It's constant. Okay. The initial value of it is equal to the final value of it. That's what we mean by conserved. So total mechanical energy in general, total mechanical energy, let me write it here as total ME, mechanical energy. Total mechanical energy is conserved, okay, is conserved, meaning the sum of it is constant unless there is friction. Okay, unless there's friction, and the friction could be friction with the surface or friction from air resistance, either way. We'll look at that more. Actually, we'll look at the example of, for example, the pendulum. Remember the experiment you did last time, the pendulum. Pendulum represents a good example of how the total mechanical energy is conserved. When you swing the pendulum, you start here with gravitational potential energy, and then it will turn into, while it's falling, it will turn from gravitational G into mechanical kinetic energy, and then while it's going up, it's turning back into gravitational potential energy. Okay, gravitational potential energy here, then back to mechanical kinetic energy, and so on. So there is continuous change from gravitational potential energy to mechanical kinetic energy, and so on. That's of course if there is no friction. That's the condition there. There should be no friction there during that process. If there is friction, so if there is friction, for example, if there is air resistance here, you'll see that the pendulum will start losing its total mechanical energy until eventually it will come to a stop. Okay, it will come to a stop because all this energy has turned into what? Because of friction, it will turn into thermal energy. Remember, thermal energy is usually comes from friction. Any type of heat, so it's associated with heat, and it's associated with friction as well. Okay, friction, of course, creates heat, and heat will take part of the energy of the system and change it into thermal kinetic energy. So when you see the pendulum losing its energy, that does not mean the pendulum lost actually its energy. Okay, the pendulum has converted its energy from total mechanical energy into heat, into thermal energy. Okay, the same thing when you drive your car has mechanical energy. When you step on the brakes, what will happen? the tires in your car will apply friction. The friction will turn all the energy, all the mechanical kinetic energy into heat. So that's how you lose your mechanical energy. You do not lose energy, you just convert it. So that's what the law of conservation of energy about. You cannot create or destroy energy. You can only change it from one form to another. So sometimes we think that we destroyed the energy or we eliminated the energy. We did not eliminate it. We just changed it from one form to another. Okay, the other thing here is the equation. We need to look at the equation of mechanical kinetic energy and gravitational potential energy. The equation, and we'll focus only on the equation of those two, okay? We need to know the formula for those two, mechanical and gravitational. For the mechanical kinetic energy, let's call it E sub k. For moving object, remember, the whole idea is about doing work. So when we measure something, we measure its ability to do work. When we measure energy, how much the magnitude of the energy, we are measuring its ability to do work. So moving objects have the ability to do work based upon their movement. And what will increase their movement is what? Is two factors, the mass and the velocity, okay? Mass and velocity, okay? Mass and velocity. Now, which one has stronger effect? We know, of course, when you hit an object with the same, when you hit an object on the street, if you're riding a scooter and you're going with 10 miles per hour, you'll do less work than if you are driving 18-wheeler, okay, with the same speed. Even if you're going with the same speed, 10 miles per hour, and you're hitting the same object, one riding a scooter, the other one driving 18-wheeler, we know the bigger object will do more work. So mass is a factor. The bigger the mass, the bigger the mechanical kinetic energy. The other factor, which is more important, is the velocity. If you're driving your car with a speed of 10 miles per hour and you hit an object on the street, you'll be able to do work, but it will be less than if you are driving your car with 20 miles per hour or 30 miles per hour. So the faster you are going, the more work you can apply on objects. The velocity is a more important factor, that's why it's squared. Okay, meaning if you double the velocity, you will quadruple the kinetic energy. Okay, if you triple the velocity, you'll increase the kinetic energy 9 folds, 3 square, 3. If you triple the velocity, you'll increase the kinetic energy 9 folds because 3 square is 9. Okay, so there is a square here, and there is the constant, which is 1/2. We found that in order to calculate the kinetic energy, you have to multiply the mass of the object by the velocity square, then multiply them by 1/2. So this is the equation for mechanical kinetic energy. The bigger the mass, the bigger the kinetic energy, the bigger the velocity, the bigger the kinetic energy. And velocity has stronger effect than the mass. Okay. Now, how about the gravitational potential energy? What does it depend on? We know gravitational potential energy is energy stored in the object due to its elevation, due to its height. So one important factor is the height, right? The further you raise the object, the more it will be able to do work when you release it, right? If you raise an object 10 feet above the ground and you release it, it will be able to do work when it hit the ground, when it hit anything on the ground. But if you raise it, instead of 10 feet, if you raise it like 30 feet or 40 feet, it will be able to do more work, right? So the height, the elevation, how far you elevated, will have a strong effect on the gravitational potential energy. The other factor is what? Is the weight of the object, right? If you raise an object that is 10 pounds and release it, it will do work, but the work will be less than if you raise a 100 pounds object. The 100 pound, when you release it, it will do more work than the 10 pound. So there is the weight, and we know the weight is mass times g, mass times the acceleration due to gravity. So those are the two equations that are important here. And those are the two equations we need to know for this lesson number 8. The equation for mechanical kinetic energy, and you need to understand those variables, mass and velocity. And the equation for gravitational potential energy, which has to do with the weight and the height. Notice here that, of course, g is a constant, 1/2 is a constant, so the main factors are the mass in both equations. The mass is a factor. For mechanical kinetic energy, it has to do with the speed mainly. Okay, so mechanical kinetic energy, the factor that will decide its value is the speed, velocity, v. While for the gravitational potential energy, the main factor is height. So gravitational potential energy is always associated with height. H stands for height here. Let me write it here on the side. H stands for height. While v, of course, we are familiar with v. V is velocity. For mechanical kinetic energy, it's associated with the velocity. So you can see here with the pendulum, you start with what? You give it height first. Remember, when you did the experiment over the pendulum, you raise it certain height first. That's how you stored its gravitational potential energy, the height. Of course, the height came from your body. Your chemical potential energy enabled you to raise the pendulum to a certain height. So you transferred your own chemical potential energy into gravitational potential energy in the pendulum. And now when you release it, the height will change into what? Of course, here at height, when you raise it to a certain height, the velocity is what? The velocity is 0. You just raise it to a certain height before you release it. Now, when you release it, the height will turn into what? The height will turn into velocity, right? Into speed. So here, what will happen in the first stage, if you call this one while it's falling, if you call it the first stage here, in the first stage here, gravitational potential energy, which is height mainly, is turning into mechanical kinetic energy, which is speed. Okay, stage number 1. Until it reaches its maximum kinetic energy at the bottom of the swing. At the bottom of the swing, velocity is maximum. Velocity here will be maximum at the bottom of the swing, while the height will be 0. At the bottom of the swing, the height will be 0. The height with respect to the elevation of the pendulum here. Then after that, in stage number 2 here, while the pendulum is going up, the opposite will happen here. So in stage 2, the speed, which is the mechanical kinetic energy, the speed is turning into height, into gravitational potential energy, into height. Okay, that's stage 2. And then backward, and so on. So after that, while it's falling down, it's turning into mechanical kinetic energy, then gravitational potential energy, and so on, back and forth. And that's actually, if you look at the PowerPoint slides in that chapter, it will show you some demonstration over that. The same thing for object, for example, going down an incline. The same thing will happen when you release it. You release an object down an incline here. Suppose you have an incline, and you release an object down an incline, and then you have here another incline. Assume this object will go down, and then it will rise above another incline here. So initially, while you are holding the object up, it has height, so it has gravitational potential energy since it has height. When you release it, the height will turn to speed. Okay, so here the gravitational potential energy is turning into, while it's falling, the gravitational potential energy is turning into mechanical kinetic energy until it reaches its minimum height here, where the gravitational potential energy will be 0 because the height is 0, while the mechanical kinetic energy will be maximum, max, because the speed is maximum. The speed here is maximum. Then if you let it continue moving and going up another incline, it will go up that incline. So now while it's going up the incline, stage number 2 here, where the mechanical kinetic energy will be turning into gravitational potential energy because the speed of this object will be turning into height, back to height here. And so on. If you let it go back, it will go back to exactly the same height here, back and forth, assuming there is no friction. It will continue moving forever, back and forth. This object will go up and down forever, assuming there is no friction. But of course, we know in the real world, we have friction. So eventually this object will start losing its energy. So it will gradually lose height, and slowly it will come to rest, because all this total mechanical energy, will eventually turn into what? Into thermal kinetic energy, Okay, mechanical energy has turned into thermal kinetic energy due to friction. When there is friction, okay. But if there is no friction, let's say we are doing this experiment on an air track where there is a cushion of air, okay, it will continue going up and down forever. Ice, okay, since the condition is icy these days. So if you release something on ice, it will continue just going back and forth on the ice, because ice friction is very, very small on ice. Okay. If you look here, we covered, let's see, so we explained the law of conservation of energy, we define mechanical and energy and explain the condition of its conservation. Remember, it's conserved whenever there is no friction. The total mechanical energy will be conserved. And recall, guys, total mechanical energy is mechanical kinetic energy plus gravitational potential energy. It's not the 7 categories, it's only 2 subcategories from among all those 7 subcategories. Okay, we explained the quantities that vary the value of the mechanical kinetic energy. Remember, it's velocity, mainly velocity and mass. And explain the quantities that vary the value of the gravitational potential energy. It's height, mainly height, and of course mass, because it's mgh equal to weight times height. Okay. And now let's solve problems that involve mechanical kinetic energy and gravitational potential energy. Notice here this schematic here actually shows you all the, as we mentioned, the energy conversion that starts from the sun, the nuclear potential energy that comes from the sun. Okay, it turns into electromagnetic radiation, light, the light that reaches from the sun. The light is used during the photosynthesis, to turn, to enable plants to store vegetables, fruits, and so on. So that's the chemical potential energy. Of course, this energy is used by us humans, by plants, by animals. We eat it, and we turn it to another type of chemical potential energy that enables us to do work, to do mechanical kinetic energy. Okay. And during this process, of course, we might lose heat due to friction and so on. So it turns back into electrical radiation. And there are, of course, several devices like solar cells that change electromagnetic radiation, light, into electrical kinetic energy. We have batteries, whether it's wet battery or dry battery, that change chemical potential energy into electrical energy. Okay. When we charge the battery, we are changing the electrical energy into chemical energy. Okay. When you charge your battery and your phone or whatever, you are changing electric energy into chemical energy stored in the charger, in the charging bank, and so on. Okay. So this kind of shows you here the array of conversions. And the light bulb, of course, when you turn the lights on, you're changing electrical energy into light. Electromagnetic radiation, guys, is light. Okay, remember, electromagnetic radiation here talks about light. Okay, and yeah, we saw here the example of the sun used in photosynthesis by plants, gives food. we can do mechanical energy, and we sweat. We turn the mechanical energy into electromagnetic radiation, to light. Of course, whenever you are in a room with many people, you notice the temperature will increase, right? If you are crowded in a crowded room, the temperature will increase. Why? Because all of us are emitting electromagnetic radiation in the form of what? In the form of infrared IR. We all bodies, whether it's living bodies or inanimate bodies, we all, as long as our temperature is above zero, absolute zero, we emit infrared, IR, infrared. Okay. Those are here the types of energy units. Okay. As we mentioned, the metric unit is joule. But we have other units here that are used by the metric system, and also by the British system. Calorie, that's different from food calorie, by the way. Calorie, or normal or regular calorie, is the amount of heat needed to raise the temperature of 1 gram of water 1 degree Celsius, and it's equal to 4.18 joules. Okay. This is different from food calorie. Food calorie is 1,000 regular calories. Okay, so when you talk about food calorie, one food calorie is equal to 1,000 regular calories. Okay, regular calories. So one food calorie is equal to 4,180 joules. One food calorie is equal to 4,180 joules. Okay, joules. Okay. The BTU, British thermal unit, is the amount of heat needed to raise the temperature of 1 pound of water 1 Fahrenheit, 1 degree Fahrenheit, and that's equivalent to 1,055 joules. There's also kilowatt hour, which is the unit used by the electric company. When the electric company charges us, they charge us with kilowatt hour. And kilowatt hour is equal to 3.6 million joules. Okay, 3.6 million joules. And of course, the cost is around 12 cents or 13 cents right now per kilowatt hour. So that's per kilowatt hour. Natural gas, we know that this is fossil fuel here, and fossil fuel is the source of energy. Of course, fossil fuel was what, so fossils, we know the term fossils are old things that basically turn into fossils. So it could be dead plants, dead animals, dead humans, and so on. Gravitational energy was stored inside the earth, condensed with time. Natural gas, we sell it in cubic foot. And 1,000 cubic foot can release 1 billion joules. Okay, 1 billion joules. Barrel of oil, we sell it in barrels, and 1 barrel is 42 gallons. And this will release 4.8 billion joules of energy. Coal is sold in tons, and 1 ton of coal can release 26 billion joules. 26 times 10.9, that's 26 billion joules. This is just to give you perspective how joule, the unit joule, is related to the units that are used usually in economy, in daily life, and so on. So let's look at some examples here, and I'll focus on the problems that involve math, because that's the part where most students have issues. If you have car B is traveling twice as fast as car A, but car A has 3 times the mass of car B, which one has greater kinetic energy? And here we are talking about, just to be exact, here we are talking about, since it's moving cars, so we are talking about mechanical kinetic energy. Okay, since we are talking about moving objects. Moving objects has to do with the mechanical kinetic energy, because we know there are 4 types of kinetic energy. There is thermal kinetic energy, there is electromagnetic radiation kinetic energy, there is the electrical kinetic energy, and then we have the mechanical kinetic energy. Moving objects has to do with big objects have to do with mechanical kinetic energy. So which one has bigger kinetic energy? Car A or car B? Notice that car B has twice the speed of car A, but car A has 3 times the mass. So which one will overcome? 3 times the mass or twice the speed? So let's look at the equation first. And from the equation, we'll be able to tell. So we know the equation for the mechanical kinetic energy, which we call E sub k, is 1/2 times the mass of the object times the velocity square. Okay, so that's the equation we know. Now let's apply it on car A and car B. So we have car A, and then we have car B. So car A, in terms of, let's call its mass, let's see here, the mass of car A. We'll call it what? Since it tells you that car A has 3 times the mass of car B, so if we call the mass of car B M, if we assign it M, car A will be what? Car A has 3 times the mass of car B. So what should we assign car A? We should assign it 3M, right? If we assign car B the symbol M, we'll assign car A 3M. If we assign, let's say we assign instead of 3M here, let's say we assign car A, we assign it to M. So in that case, car B will be what? Car B will be what? Will be 1/3 M. Because car A is 3 times the mass of car B. Okay, so it's up to you. You can assign car A M. In that case, car B will be 1/3 M. Or you can assign car B M. In that case, car A will be 3M. Okay. I prefer to avoid fraction here, just to make the calculation easy. I'll avoid using fractions. So I'll go with assigning car B mass M. Hence, car A has will be assigned 3M. Okay. There's no numbers here. You're not given numbers, so you have to deal with symbols. Okay. The other thing here, the speed. Let's look at the speed. It tells you that car B traveling twice as fast as car A. Twice as fast as car A. So if the speed of car A is V, what would be the speed of car B? What should be the speed of car A based upon car A? Since car B is twice as fast as car A, so if car A has speed of V, then car B has a speed of 2V. Okay, we'll assign it 2V. So this is how you deal with these problems that do not give you numbers. Okay, there are no numbers here. You have to deal with symbols. You assign one of the objects a certain symbol. You assign the other objects a symbol that is relative to the symbol that you assign it to the other object. So V2V, M3M. Okay, and now we can apply the equation and compare the formula. So now we'll apply this equation. So for car A, the kinetic energy of car A. Okay, so car A kinetic energy will be what? 1/2 times the mass of car A times the velocity of car A squared. Okay, so it's 1/2. The mass of car A, we give it we assign it the formula 3M. So mass of car A is 3M. And the velocity of car A is what? Is V. So it's V squared. Okay. So this will give you what? This will give you for car A, it will be 3/2 M V squared. So this will give you for car A, it will be 3/2 mv squared, right? 3 times 1/2 is 3/2 mv squared, or 1.5. You can write it as 1.5. Now we'll do the same thing here for car B. So this was for car A. For car B, the kinetic energy is 1/2 the mass of car B times the velocity square of car B. So now we apply the equation. This is basically 1/2. The mass of car B is just M. And the velocity of car B is 2v, so it's 2v. And guys, this is the trick here, okay? This is where most of the errors take place. The square, since the equation is velocity of car B squared, the square is applied. Is it applied on v only or 2 times v? It will be applied on both v and 2. So this whole thing is the velocity of car B. So the square is applied on the 2 and on the v, okay? So now if you carry out the calculation for car B, just by applying this formula, it's basically 1/2 times the mass. 2 square is what? 2 square is 4. So it's times 4. And then times v square. Okay. So if you continue here, we know 4 times 1/2 will give you what? Will give you 2 mv squared. So notice here, this is the kinetic energy of car B based upon the symbols we used here. And this is the kinetic energy of car A, 3/2. Which one is bigger, 2 mv squared or 3/2 mv squared? Which one is bigger? Of course, 3/2, remember, 3/2 is 1.5, right? 3/2 is equal to 1.5. So which one is bigger? Here, m and v squared are common denominator. Both of them have mv squared. The difference is in the coefficient, 3/2 and 2. You can see, of course, 2 is bigger than 1.5. So car B has bigger kinetic energy. Okay. Car B has bigger kinetic energy, and that's because car B has twice the speed of car A. Now, yes, car A has 3 times the mass, but we learned that the speed has more influence. Okay, the speed has more influence than the mass. So when you square the velocity, this will give you more effect. So if you increase the velocity twice by 2, this will increase the kinetic energy by 4, because 2 squared twice means times 2, right? Twice means you are multiplying it by 2. So the kinetic energy will increase by what? By 2 squared, okay? By 2 squared. So you're multiplying the kinetic energy by 2 squared, which is basically you're multiplying it by 4. So this will increase it 4 times compared to mass. Mass will be just the 3 times that you multiplied by, okay? Let's look at another example. I know this might be something new. You never did this type of reasoning before. So let's look at another example here. Let's look at the problem number 8 here. Which one of the following objects has greater kinetic energy? And I want you kind of to make a guess here. Just try to decide which one of those choices. You have 4 choices. Which one of them has the greatest mechanical kinetic energy? Remember, the equation of mechanical kinetic energy is equal 1/2 the mass times the velocity square of the object. So apply this equation on all those choices, choice A, choice B, choice C, and choice D, and determine which one of them has the biggest mechanical kinetic energy. And remember, guys, when you square the velocity, you don't square only the v, you have to square the v and whatever the v is multiplied by. Like here, you square 2v squared, you square the 2 and the v. The same thing here, you square the 3 and the v. Here, you square the 4 and the v as well. Yeah, I see most of the answers are around two options, and one of them is the correct option. That's correct. Okay, and I would like answer also from those that are not on cam, so that just to know that you are present. Okay, just to make sure you are present. Just those that are not on the camera, just give it a guess. Okay, guys. This will at least tell me that you are present here. All right, let's do it here. And by the way, question number 8 is the same as question number 14. It seems because I like this question, I put it twice. Okay, so for the first choice, We'll apply the equation, so it will be simply E sub k equal 1/2. We're applying this equation here. So for the mass, it's just 4m, so I replace the mass by 4m. And for the velocity, it's just v. So it's v here, square. So this will give you what? 4 times 1/2 will give you 2. And then you're left with mv squared. Okay, so that's the final formula for choice A. That's the final formula, 2mv squared. Let's compare it to the final formula of B. Okay, for B. So we'll do the same thing here. The kinetic energy of option B will be 1/2. We're applying this equation again. The mass in option B is 3m. So let's multiply by 3m. And the velocity is 2v. And recall here, 2v, the square, v square here in the equation, the main equation is applied on everything that represent v. So it's the 2 and the v. They are all squared. Okay. So this will give you what? 1/2 times 3 will give you 3/2 times m times 2 squared, which will give you 4. Of course, here the square is applied on both the 2 and the v, and then v square. You can see here 4 times 3/2 will give you what? 2 will cancel out to the 4. 4 will become 2, so this will give you 6 m v square. Okay, guys, 6 m v square. Okay, because 4 divided by 2 will give you 2. 2 times 3 will give you 6. So you can see here, option B, we know option B is bigger than option A. Now let's look at C. We're applying the equation, E sub k, 1/2. Now the mass is what? The mass is 2m, so we'll use 2m here. And the velocity is 3v, and it's all squared. So this will give you, now 2 divided by 2 will give you 1. So we have 1 times m times 3 squared, which is 9, times 9, times v squared. Okay, so you can see here it's 1 times m times 9 times v squared, which will come out to be 9m v squared. This is 9. Okay, so you can see here so far the one with the highest kinetic energy is option C. Now let's look at option D here. The same thing, 1/2. Now the mass here is just m, and the velocity is 4v. So we have to use 4v all squared. We have 1/2 times m. Now the 4v, 4 squared will give you 16. Okay, this 16. And v squared will give you v squared. You can see here 16 divided by 2 will give you what? 16 divided by 2 will give you 8, right? So this will give you 8 mv squared. So now if you compare the formula of C to the formula of D, which one is bigger? Notice here mv squared is a common denominator. So we are comparing the coefficient 8, 9, 6, and 3. And we, of course, among those 4 values, 9 is the biggest. So C is the end. And yeah, the reason here, because although the velocity in D is 4 compared to 3, but if you think about it, 4 compared to 3 is not double. 4 over 3 is 1 plus 1/3. Okay, 1 plus 1/3. When you square it, it will give you what? It will give you 16 over 9. You square it, of course, the ratio here in terms of square, 16 over 9. And 16 over 9 is less than 2. The mass here is double, so C here is twice the mass of A. So the effect on the mass is bigger here, because the velocity, although when you square it, it's 1.33. When you square 1.33, this will give you 16 over 9, which is like 1.777. It's less than 2. Anyway, it's less than 2. 1.3 squared is less than 2. So the fact that mass is twice in choice C is twice the choice D will give the kinetic energy the boost needed to be bigger by a small amount, 9 compared to 8. And so that's regarding to that question here. Now let me introduce the next lesson here, and yeah, feel free guys to ask questions in the chat or email me and so on. And I went over most of those questions in the video, so make sure you go over the video. But let me here go back to just introduce lesson number 9 because we need it in the lab. Okay, we need to know about power. So lesson number 9 is about power. You are familiar with the term power. Maybe when you buy anything, a light bulb, it has a certain power rating, like 90 watts, 100 watts, 60 watts, and so on. Usually, for big machines, they use horsepower. Okay. So what is power? Power basically is the amount or the rate at which the work is being done, the time rate at which the work is being done. So for something to have big power, it's not enough to do big work. It's not enough to spend a lot of energy. You have to do it at very fast rate, okay? How fast you are expending energy, how fast you are doing work. So power is defined as work over time or energy over time. We know work and energy can be exchangeable. So yes, this is work over time or energy over time. How fast you are spending energy or how fast you are performing work. So you can see power is inversely proportional to the time, meaning the longer the time it takes, the less the power. Okay, the longer the time, the less the power. And unit of power, as you see in terms of units, we know energy is in joules, and we know time is in second. So the unit of power is joule per second. Joule, it's a joule. Joule per second, which we call it watt. Okay. So for example, if you have, let's say, a 100 watt light bulb, what does that mean? 100 watt light bulb, this means this bulb has the ability to dissipate 100 joules of energy per second. Okay. 100 watts means this device, this light bulb, has the ability to use 100 joules of energy per second. Okay, that's the meaning of watt. How much energy can be used per second? So watt is joule per second. Okay. We learn also another unit which is called horsepower. And usually we use horsepower for machines. Horsepower was first used in coal mines because they used to use horses to lift the coal out of coal mines. So they calculated the horsepower, and 1 horsepower is equivalent to what? To around 746 watts. So to convert from watts to horsepower, you have to basically divide by 746. Okay, to convert from watts to horsepower, you have to divide by 746. So yeah, this information we need for the lab, because in the lab you'll be calculating your power and your horsepower. So I'm introducing this introduction here first before we start the lab today. And this is actually the lab we'll be doing today. I mean, all this problem represents the lab we are doing today. So first here in this problem, suppose how much power is required to lift a kilogram mass a distance of 1 meter. So notice here you are asked to find the power, but to find the power you need to find the work first. And to find the work, you have to find the force first. Okay, so although you're asked to find the power, there are 2 steps before you find the power. You have to determine the work, and in order to determine the work, you have to find the force. Okay, So you have to start with the force. And here, since you are doing force against gravity, because you are lifting the object, so the force will be the weight of the object, mg. So the first step is to find the weight of the object, which represents the force you need to exert in order to lift that object, mass times g. So 1 kilogram times 9.8, this will give you the force. So this equation for the force. Then you have to multiply it by the distance to get the work. And the distance is 1 meter. So you'll multiply it by 1 meter. So now you'll get the work. So we got the force first, then we got the work. Then after that, you have to divide it by the time. And the time here is 1 second. So here we just merged the 3 steps in 1 step. Okay, you can do it in 3 steps, maybe easier. And we got 9.8 watts. So let's see that on problem number 1, because problem number 1 is very similar to the lab we are doing today, this week. So here, a 130-pound student races upstairs with a vertical height of 8 meters in 5 seconds to get to the class. On the second floor, how much power in watts does the student expend in doing the work? Now notice here, you are given the weight in pounds, and in the experiment, you'll be actually converting your weight in pounds to Newton. So the force has to be in Newton. And we know that one Newton is 0.225 pound. Okay, 1 Newton is 0.225 pound. So first step, in order to find the weight in Newton, you have to convert 130 pounds need to be converted to Newton. Okay, so to do that, you have to multiply 130 pounds by the conversion factor that will cancel out pounds. So you need pound in the denominator and Newton in the numerator. And we'll basically input the values here from the conversion statement. This is the conversion statement. 1 pound is 0.225. 1 Newton is 0.225 pound. So we place 1 beside Newton, 0.225 beside pound, and then you can use the calculator to do the division here, and this will give you 577.8 Newton. If you round it off, 577.8 Newton. So now you have the force in Newton. You can calculate the work. So work is force times distance. So work will be 577.8 Newton times the distance, which is given to be 8 meters. 8 meters, right? And if you carry out the calculation, this will give you 4,622 joules. 4,622 joules. And then to find the power is work over time. So you divide 4,622 joules by the time, which is 5 seconds. You can see it will give you around 924 watts. And you can convert it to horsepower by dividing it by 746. If you want to convert it to horsepower, and that's what we'll be doing in the experiment, you'll divide this power by horsepower, 746. So this will give you around 1.24 horsepower. Okay, here in this problem, you're not asked to convert it, but if you're asked to convert it, this will be around 1.24 horsepower. Okay, so if we go back to week number 5, so we'll get out of the quiz folder and we'll go to the week folder. We'll go to the week folder, and then in the week folder, we'll click on the lab folder, which is experiment number 5. It's titled experiment number 5, work, power, and energy. We'll click on it. Now, notice here in this lab, there will be 2 documents that you need to download. There will be the procedure, and also there will be a worksheet. So if you click on the procedure, it will download the procedure. I'll show you here. Okay, so that's the procedure for the lab. Where you need to follow the steps there. This will be a physical lab. It's not virtual labs like the previous labs. So you have to do activity. The activity will require a ruler or measuring tape. So it's basically tape, measuring tape or ruler. Okay, or ruler. Or meter stick. Well, I already have that. Okay. Yeah, I already have it right. Okay. Tape, measuring tape, ruler, or meter stick, and then stopwatch. So you need those two items. Okay, something to measure with, measure length, and something to measure time. Okay, stopwatch. You can use, of course, the stopwatch on your cell phone. Okay. So those are the two things. And also you need a third thing, which is a staircase. Okay, a staircase. A lot of stairs. Okay. And then you'll be, make sure to read the background here, the equation you'll be using. Okay, of course, 746. And in this lab, you'll be walking up or running up flight of stairs. Okay. Now, if you don't have a staircase in your house or in your apartment complex, if you don't have a staircase, you might need to go to a nearby building that has stairwell. TCC has Southeast Campus has several staircases, stairwells you can use. Okay, and if you cannot drive right now, I mean, hopefully the temperature will go down according to the forecast by the weekend. Yeah, Saturday or Sunday. But if you need extension, let me know. Email me. If you just cannot make it on Saturday or Sunday, you need to go Monday or Tuesday. Because of course I would not. If you don't have staircase in your house, I would not recommend doing this experiment during these weekdays. Okay, it will not be safe until maybe Saturday. The temperature will go up. Yeah, the whole Saturday will be above freezing. So you can do it Saturday or Sunday. But if for whatever reason you cannot do it during the weekend, you can wait till Monday. Okay. So just let me know via email if you need the extension till Monday. Okay. That would be fine. But yeah, basically we'll be running and walking a flight of stairs. And then you'll be completing the table in the worksheet. And I have here some videos that shows you example of how this experiment was done. So make sure you watch those two videos. And then you need to answer those questions. So let me go to the worksheet and show you the worksheet you have to fill out. So this is the worksheet here. In the first part here, you record your weight or your mass in pound, okay? By the way, mass or weight, both here, pounds, this is in pounds. So for example, if somebody weighs, let's say 200 pounds, then make sure you write everything in red. It asks you to use red font, so make sure you turn it to red. To convert it basically to Newton, as I showed you in the problem we solved a few minutes ago, you have to multiply it by the conversion factor that has Newton in the numerator and pounds in the denominator, so that pound will cancel out with pound. So if somebody weighs 200 pounds and you divide by 0.225, this will give you around 890. Okay, so something like around 890. I'm just showing you here example with numbers. Don't copy those numbers. Okay, this is just applied on someone that weighs 200 pounds. Okay, 800 Newton. And guys, I mean, no one will see your weight in pounds except me, and I will not tell. Okay, so no worries there. Now, how can you calculate the height of the flight of stairs? You need to figure out the height of the flight of stairs. Now, if you have a ruler, small ruler, of course, you cannot measure the whole height. So to measure the height of the flight of stairs, let me show you here. So suppose you have this flight of stairs here, and try to select a flight of stairs that has at least 10 steps, okay. 5 steps if you cannot find 10 steps, but preferably 10 steps. 1, 2, 3, 4, 5, 6, 7, 8, like 9, 10, okay, 10 steps. Suppose this is you here. Okay. To measure the whole height will be from the top to the bottom. So the whole thing here, this will be the vertical height of the flight of stairs. So how can you measure this whole thing? So what you can do here, just measure the height of one step. Let's call it h. And then multiply it by the number of steps. So d, which is the vertical height, this is d here, will be basically the height of one step times the number of steps. Okay. Now, very important here, make sure that you convert the height to meters. Okay, so this has to be in meters. And that's actually where most of the mistakes take place. Students write it in inches or in centimeter. They forgot to convert it to meters. Suppose the measuring tape you have is in inches. So suppose you measure it in inches. Suppose the measuring tape you have measure inch. So you have to convert the inch to centimeter. And then you convert the centimeter to meter. Of course, to convert from inch to centimeter, you have to multiply by 2.54. From inch to centimeter, you have to multiply by 2.54. This will convert the inch to centimeter. Okay. To convert the centimeter to meter, you have to move the decimal point 2 places to the left, or basically you have to divide by 100. Divide by 100 to convert centimeter to meter. Okay. So the height of one step should be somewhere around 10 centimeter, 10 to 15, maybe around somewhere around 0.1 meter, 0.15. Okay, that's the height of one step, somewhere around 0.1. Okay, maybe 0.15, more than 0.1, 0.1 plus, I would say. Okay, that's the height of one step. Then of course you have to multiply it by the number of steps. Okay, yeah, this is exaggerated here. 10 steps will not be longer than you. Yeah, I mean you'll be very close. 10 steps will be somewhere, maybe depending on your height, it will be close to your height. Yeah, the more number of steps you have, the better. Now here you have to write the final value, whatever the final value here. Of course, you should get somewhere between I would say 1.5 meter to 3 meters here. Okay, somewhere between 1.5 to 3 meters. Okay, if you got 30 meters, you should know that you did something wrong. Okay, 30 meters is like 10 or 15 story building. Okay, and if you got something very small like 0.1 meter, then also you did something wrong. As long as you have around 10 steps. If you could not find 10-step staircase, 5 would be fine. Also, you can use, if you have attic at your house, if your house is one-story house, you can use the staircase to the attic. Okay. Yeah, you need to have at least 5 steps. So that's the third step here, finding the vertical height. That's where most of the error take place. So I'm focusing on this point here because that's where most of the errors take place. Then you need to time yourself walking and then running up the flight of stairs. And you'll time yourself just going up. You'll not time yourself going down, just going up. Okay, because we are going to measure the work against gravity, not with gravity, against gravity. So you'll be walking up the flight of stairs, record your time here. Then you'll run the flight of stairs and you'll record your time here. So far, all those values are the same. Whether you're running or walking, those are the same for walking and running. But this one, of course, will be different. When you measure the time of walking, it's different from the time of running. The height will be the same whether you're running or walking. Your weight will be the same whether you're running or walking. The time will set the difference between running and walking, okay? How much time it will take. Now, again, as I mentioned at the beginning of the semester, if you have a physical condition that does not enable you to run, then just for walking, you'll walk slow. You'll do very slow walk. For running, you'll do faster walk. Okay. So don't worry if you have any physical condition does not allow you to run flight of stairs, then that's fine. Just walk slower compared to faster. Also, if you cannot climb flight of stairs at all, if you have physical condition that does not allow you to go up flight of stairs at all, then you can ask a sibling or spouse or parent or daughter or son to do it for you, and you'll time them, okay? So no worries there. Then after that, after you got the time, now you need to calculate. Now the calculation will start, okay? So far, those are measurements. And now here the calculation will start. Okay, now for the work. To calculate the work done, you'll take your force in Newton. So it has to be the force in Newton, which is this one here, and multiply it by the distance, the vertical height, which is here the distance in meter. So you multiply rho 2 by rho 3 here. Multiply those two. You'll multiply them by each other to get the work. This will give you the work. Okay? It's force times distance. And you'll do it for running or walking. For running and walking. Now, do you expect the work done for running and walking to be different, or will it be the same? Now notice the work is the force, the weight, basically your weight times the vertical height. You need to ask yourself, would the force be the same, whether you're running or walking? Would the distance be the same? Because the only way the work would be the same if distance is the same, whether you're running or walking, and if the force exerted is the same. In order to walk or run a flight of stairs will be equal to what? The force is equal to your weight will be equal to your weight. Assuming you are running and walking at constant speed. In both cases, you are going with constant speed. Of course, initially you have to push yourself, so there is acceleration for a second, or for fraction of a second to push yourself. But then after that, you are either running at a constant speed or walking at constant speed. So the force would be balanced with your weight. Force is equal to weight. Would your weight change whether you're running or walking? Your weight is the same. Whether you're running or walking, it's the same weight, right? Your weight will not change. And the same thing for the distance. You're going the same flight of stairs. Running or walking will be the same distance. You're not changing the distance. So I'll let you see that when you do the experiment. And that's actually our confusion between work and power. For power, you'll take the work that you calculated in the previous step and you'll divide it by the time. And of course, now time will make difference because time walking will be longer than running. So time will be the difference. This will make the difference between running and walking. It's not the work, it's the power, because time is different. So time will be different. Of course, it will be shorter for running. And the shorter the time, the bigger the power. The shorter the time, the bigger the power. So you expect running to give you more power. So we are doing right now the prediction. We are doing the hypothesis part. Okay, so you calculate the power by dividing the work here that you calculated by the time. Of course, for running, it will be different from the time of walking. We'll divide the work by the time, divide here, to get power. So you get, this will give, of course, when you divide joule per second, this will give you watts for power. And then to get the horsepower, you just need to divide by 746. So to go from watt to 740 to horsepower, you'll divide by 746 because 1 horsepower, as we learned, 1 horsepower is 746 watts. After you complete the table, there will be the questions, but before you answer the question, there are a few things I want you to include in your report sheet here. You need to show a sample calculation for each one of those. So for calculating the force in Newton, which is this step here, how you calculated the 890, for example, you need to show the calculation here, just one sample calculation. For calculating the work in joules, and make sure when you show the calculations to show the values and the unit beside them. Make sure to include the units. So the units need to be in the final answer, and also they need to be beside each numerical value. Each numerical value has to have units. Just to give you an example here, in order not to lose points, guys, I just want you to get all the points. So for example, here to show sample calculation of the Newton, suppose if your weight is 200 pounds, you're multiplying 200 pounds by the conversion factor that has pounds in the denominator, Newton in the numerator, and one Newton is 0.225 pound. You'll show here that, of course, pound will cancel out with pound, and you'll get 890 Newton, for example. And you can show here that those units will cancel out. Here, pound will cancel out with pound. Okay. The same thing here for this calculation. Suppose you're calculating the work in joules. So you take, so the work in joules here will be 890. So the work in joules here will be 800 Newton times, so suppose the distance came out to be 2 meters. This is work, this is W, by the way, this is W. So 890 times 2 meters, Newton times meter will give you joule. And 2 times 890 will give you 1780, right? Joules, okay? And so on. You do the same thing for watts. You'll take whatever here, suppose for watts, the power, you'll divide the work, which is 1780 joules, by the time. Let's say your time of running was 2 seconds. So 1780 divided by 2 seconds, which will give you 890 watts. And then you convert the watts to horsepower and so on. So make sure you show this is second, by the way. Yes, second, and this is joule. Okay, and so on. So make sure you include all the units in your calculation. So the other thing I want you to include in your report sheet is photos. This will enable you to assess the height of the staircase. So you need the 2 photos. The first photo should display the staircase. So you can take a selfie here. So basically what you can do here, take a selfie where it shows the staircase behind you. Okay, so this is basically a selfie where you show yourself and the staircase behind you, the whole staircase. Okay, make sure that the whole staircase behind you. Okay, this will enable me to assess the height of the staircase. So if you write 2 meters and I see only 2 or 3 steps, I know you got it wrong. Just want to make sure that you are there, you're not taking the picture out of the internet. Okay, so selfie that include you, you have to be in the picture, the photo, and the staircase behind you. The second photo should show you while you are measuring the length of one step, of one of the steps. So again, it can be a selfie. You'd just be holding a ruler. So suppose you don't have to show yourself. Just show your hand here. Your hand holding the measuring tool, for example, the ruler. Okay, and just take a picture of yourself, of your hand while holding the measuring tool. Okay. While holding the measuring tool, whatever the measuring tool is, if you're using ruler, measuring tape, whatever it is, okay? So those are the 2 photos, make sure to include them here, okay? So that's you'll complete this the sheet here, and then you'll save it after you complete it. And guys, make sure you use red font again, red font here. The calculation does not have to be in red font, okay? You can, by the way, for calculation, you don't have to use, if you can use the mathematical equation, if you're familiar with using equation, you can do that. Or if you cannot use equation, just use something like, 890, you can type 890 pound divided by 2.25, and you can write here pound per Newton. Okay, and then type the answer, whatever, like 890 Newton, and make it red if you can. Okay, it's red. Okay, so something like that would be fine. Okay, as long as I can see units and the right operation, I can see division. So after you complete the whole thing here, save it to your hard drive. So click File, and then click Save. Okay, so that you can save it as, and save it whatever. Just make sure you save it to a name that you can identify, because I don't want you to attach or to submit the wrong document. Okay, as what happened with a few of you during the first experiment. So I want you to make sure you submit the right thing. Okay, and after that, when you're ready to submit it, you can click here on the link, experiment number 5, click on it, and then it asks you, are you ready to take the lab assessment? So click begin, and you'll be submitting your worksheet in the first question here. So the first question, submit the completed experiment number 5 worksheet, the report sheet document. So you click browse my computer. If you save it to your computer, you click browse. You look for your the file that you saved. Okay, so guys, look for your document. Click on it, save it. It was 14 points, so that's actually more than around 70% of the grade is the worksheet. Then you have to answer those questions here. How does the work done in running the stairs compare to the work done walking the stairs? So you compare the work done running to walking. Then question number 3, explain your answer in the previous question. So you'll select the choice that represent the rationale for your answer in the previous question. Then question number 4, explain why there is difference between the horsepower in walking compared to running. And then question number 5, could a horsepower developed by a slower student be bigger than a faster student? You need to explain why in the next question. And then question number 7, how the work and the energy related. So of course, guys, everything is based on the procedure. So make sure you read the procedure part carefully. Go over the background information and so on. I mean, if you have staircase, you can try to work on this experiment before Wednesday. All right, if you have staircase in your house, maybe try to submit 1 attempt by Wednesday if you can. Okay, if you have staircase available and accessible to you. All right, so again, the same thing, you'll be submitting this lab assessment. This is the lab assessment you submit. But of course, the first question in that lab assessment is to submit the report sheet that you need to complete. Okay.